Good morning, champs. In the previous videos, we introduced the boundary layer, developed velocity profiles, and derived the von Kármán integral equation, starting from the governing equations. Now we combine everything to solve a real boundary layer problem step by step. We consider a flat plate in a steady incompressible flow with constant free stream velocity u infinity. A boundary layer develops along the plate. We use the polynomial velocity profile. U over u infinity equals 3 halves times y over delta minus 1 half times y over delta cube. First, we compute the wall shear stress. From Newton's law of viscosity, tau equals eta times du dy. We differentiate the velocity profile with respect to y. This gives du dy equals u infinity times 3 halves divided by delta minus 3 halves times y square divided by delta cube. At the wall, where y equals 0, this simplifies to tau wall equals 3 halves times eta times u infinity divided by delta of x. This is an important result. It shows that a thinner boundary layer leads to higher shear stress. Next, we compute the momentum thickness. The definition is delta 2 equals the integral from 0 to delta of u over u infinity times 1 minus u over u infinity dy. We insert the velocity profile. To simplify the integration, we introduce a new variable, eta equals y over delta, which gives dy equals delta times d eta. The integral becomes delta times the integral from 0 to 1 of the polynomial expression. After carrying out the integration, we obtain delta 2 equals 39 over 280 times delta. So the momentum thickness is proportional to the boundary layer thickness. Now we apply the von Kármán integral equation. d delta 2 dx equals tau sub w rho u infinity square. We insert delta 2 equals 39 over 280 times delta. This gives 39 over 280 times d delta dx equals tau wall divided by rho u infinity square. Now we substitute the expression for the wall shear stress. Tau wall equals 3 halves times eta times u infinity divided by delta. This gives a differential equation for delta of x. We rearrange delta times d delta dx equals 140 over 13 times eta divided by rho u infinity. We integrate both sides. This gives 1 half delta square equals 140 over 13 times eta divided by rho u infinity times x. Solving for delta, we obtain delta of x equals the square root of 280 over 13 times eta divided by rho u infinity times x. This is the key result. The boundary layer thickness grows with the square root of x. Finally, we look at the shear stress behavior. Since tau wall is proportional to 1 over delta, and delta grows with the square root of x, we find tau wall is proportional to 1 over the square root of x. This means the shear stress is highest near the leading edge and decreases downstream. Let us summarize. We assumed a velocity profile, computed the shear stress, calculated the momentum thickness, and used the von Kármán equation to determine the boundary layer thickness. This method allows us to solve boundary layer problems without directly solving the full Navier-Stokes equations, while still capturing the essential physics.